In the last lecture, we were discussing the theory to explain why ice ages occur every 100,000 years during the last million years. Okay. We found that if you propose a simple linear model, that the temperature variation in the polar region is directly related to the incoming radiation in the polar region in summer, then we have a problem, which is that the largest amplitude of variation of radiation from the sun occurs in the 20,000 year cycle, while the observed amplitude of the temperature variation in the polar region is in the 100,000 year cycle. So, we have to conclude that the linear system model cannot be right. If the linear system model was right, the forcing amplitude of solar radiation is maximum at 20,000 years, then the temperature should fluctuate with a 20,000 year cycle. It is not fluctuating. It is fluctuating more closer to 100,000 year cycle. And so, the only way to resolve the issue is to propose a nonlinear model. So, I briefly discussed this nonlinear model of Salzmann, in which he said the rate of change of ice, which is in x here, and the rate of change of deep ocean temperature, which is close to global mean temperature, and the rate of change of carbon dioxide, they are interconnected, interrelated, and each of these equations also had a nonlinear term. So, by putting these nonlinear terms in this equation and having a coupled, three coupled ordinary differential equations, Salzmann solved this problem and he got the following result for the last 200,000 years, in which the model simulation in black agreed fairly closely with the ice core data. Okay. Not perfectly, but quite closely. The peaks are matching. Okay. Now, he did one more simulation. This is only for 200,000 years. He followed this up with another simulation for 400,000 years, where the black is the simulation and red is the observation. Here blue is the ice mass, here red is CO2. So, this model is able to predict that both CO2 and the amount of ice on earth will fluctuate with a 100,000 year cycle by incorporating nonlinear terms in those three equations. But the only problem with that model is that those terms which were introduced by Salzmann are essentially ad hoc. They do not follow directly from either energy balance equations or mass balance equations or some other conservation law. So, these are postulates that, for example, the temperature depends quadratically on the temperature and the ice mass depends quadratically on temperature and the deep ocean temperature depends quadratically on ice mass. So, these are hypotheses which is not easy to prove. So, although Salzmann managed to get fairly nice results, people still had doubts about whether this hypothesis was valid. Okay. The other problem people had was that there is ice over land and there is ice over ocean, okay, that is sea ice. Now, what happens is that the land ice builds up very slowly over a 90,000 year period and then rapidly. And what you see here is that at that time the sea ice is not changing much. The sea ice increases rapidly only near the end of this period, and the same way when the land ice starts decreasing, initially sea ice change is small, then sea ice change is rapid. So the two different time scales of the sea ice and the land ice would have some impact on the 100,000 year cycle, and this was the hypothesis of Gildor and Zipperman, which has some similarities to the hypothesis given by Salzman. Okay. Now one more hypothesis of Huber, who says that yes, ice age should have come every 20,000 years, but some time the occurrence of ice age was skipped. He has not given a reason why. He is appealing to trigger. For example, you saw that there are certain threshold values of solar radiation. Only when it goes below that, ice starts forming. Okay. So his argument is that in the 400,000 year period we saw, there were periods where although the solar radiation went down, it didn't go sufficiently down in the 20,000 year cycle. So that cycle it skipped. And so in his argument, to get 100,000 year cycle, you have to skip 3 20,000 year cycle, and the fourth one it should come. So this also is a bit far-fetched, but this brings in this question of some non-linearity of the problem. Okay. See, the non-linearity, if you want to explain better, it is better done through our energy balance equation, in which we have the rate of change of temperature of the earth, heat capacity here, this is the incoming radiation, this is the albedo. So this is the absorbed solar radiation, this is the emitted radiation, which is linearized as we have done earlier. Okay. So this is outgoing radiation, this is absorbed radiation, and the difference should drive the temperature. Okay. Now the best way to understand this equation when changes in albedo could be nonlinear is to rewrite this equation based on what is called Lyapunov potential. Okay. You write the dt dt and take this side and write the right hand side as minus dV by dt, where T here is temperature. Okay. So essentially V is nothing but integral of this equation. Okay. We are just rewriting it, nothing very unusual. Now when you rewrite this way, then you plot V as a function of T, this integral, then it will have this kind of shape. The Lyapunov potential has a shape in which it has two minimas here and here. Okay. One corresponding to snowball and the other corresponding to the present temperature. And the idea is that the system switches between this state and this state depending on the perturbation coming there, noise or whatever it is, to push this over this hump and take it down here. Similarly, to go from the ice age to the present climate, you need a large push above this hump to come here. So the idea is that the trigger to push the system from one stable state to another stable state requires some external trigger, and that could come from various sources. Okay. So again, I recall to you what we discussed this when we discussed global mean temperature. This was the last ice age, this was the present climate, this was the snowball region, and we saw that this last ice age state was unstable. Slightest perturbation switched it to the either the present climate or the snowball. Okay. So this result is plotted in terms of dV dt to explain the role of potential. So essentially we are saying that to shift the Earth's climate from one state to another state in a nonlinear problem requires something to push it up to that hump which is keeping these two states separate. So once something pushes it up there, then it will move to that state. What pushes it up there could be something related to either the land glaciers or sea ice or some weather related noise. For example, you can move from interglacial to glacial if there is a major volcanic eruption which cools the earth so much that it shifts this from here to here. Some shock is given to push it up. Okay. Now the best way to understand this is by animation done by Chris Bolton of University of Exeter in United Kingdom. So here is a Lyapunov potential showing two stable states, and the earth is in one stable state here, and it continues with that. There are perturbations to this state shown by this time series here, and see the potential itself is changing on account of changes in temperature and ice cover. Suddenly the potential becomes suitable for it to come this way. So you can see that this animation represents very nicely how the earth remains in one state for a long time because this is extremely stable, but as the potential changes in response to the changes in temperature of the earth and changes in sea ice cover, land ice cover, as the potential changes, there comes a point at which the ball is able to jump over the hump. Hump is very weak here, and so the ball jumps over the hump and suddenly comes to the new state. You can see the sudden jump, right. So this is the abrupt change in climate we are concerned about, which may happen in the future. So I wanted to look at the animation a couple of times to be convinced that the earth can go from one state to another state depending on the shape of the Lyapunov potential as well as the trigger due to something like a volcanic eruption or some other noise in the system which shifts this ball. When the Lyapunov potential is of this shape, it will suddenly shift to this state. Okay. So this is a nice animation showing how even random noise can shift a system from one state to another state. Now this is given a name called stochastic forcing. That is, the forcing is not steady, it's fairly random, and it can under certain conditions shift the earth from one state to another state if the Lyapunov potential is of the right shape. Okay. So idea is that the ice age conditions change the Lyapunov potential and then some random event shifts it. So if you understand this approach, then one can justify the argument about skipping 20,000 year periods. Imagine that in one 20,000 year cycle, the conditions were such that the ball could not shift to this state, and it happened in 2 or 3 times, and in the 4th time it shifts on the other side. So the idea is that the shape of the Lyapunov potential was not the same during the various times when the 20,000 year variation of solar radiation should have triggered either the collapse of the ice age or the establishment of the ice age. Okay. So that was animation. You can also look at it without the animation, showing how as the Lyapunov potential changes shape, there comes a point at which this earth in this state can shift to this state. Okay. So it depends on both the shape of the Lyapunov potential and the perturbation that it is getting at that time. Okay. So this is another way to show that time t equals 0, 1/4, half and t. You can see that at this point the shape of the potential is such that some little kick will shift to this state. Okay. So, going from here to here, it does not shift at this point, but shifts at this point because the Lyapunov potential shape has somewhat changed compared to this. You can see again it has gone up here. So, slight this valley is steep here, it could not climb that. Here the valley is shallow, it climbed that. So, that is the logic here. Another example of the changes in Lyapunov potential, here it's in a deep well, it will never come out easily, but as the well changes shape at this point, it is suitable to change to this. Okay? And this is based on a simple algebraic model for the Lyapunov potential. Okay? So, these are good examples, but I will say the best way to understand this would be to do actual problem. So, here is example where he says the regime shift occurs when some shock, here he says sharp loss of ice due to one hot summer, okay, random event, it shifts it to the state. Okay. And this time it is more favorable than this time, okay, that is the point. Now, I think the best way for you to understand this problem in the context of this course is to solve a simple problem. Here is a problem when rate of change of temperature of the earth is written in terms of incoming radiation. This is the global wind temperature here, and the albedo written 1 minus albedo written as a tan hyperbolic function. We did this earlier, this example, and then the outgoing radiation expressed as Stefan Boltzmann's law, okay, and emissivity. Now, all of you should try to solve this problem on the computer, and you will find that depending on the initial temperature you give, if you keep 10.05 degree centigrade, it shifts to the warm state, 15 degrees centigrade, present climate. If you give a slightly lower value, 0.01 degrees lower, it will shift to the glacial state, around 4.5 degrees. So, this equation is very sensitive to initial condition. So, whether the system will shift from the ice age condition to snowball or present climate depends on the temperature during that ice age. And you can see a small change in temperature of 0.01 degree will shift it here or there. So, this shows the impact of stochastic forcing. If the system is sitting very close to an unstable equilibrium, a slight push will shift to that side. Okay. So, you can solve this equation, and today all of you will have access to software. You will solve this nonlinear equation by marching in time. It is very simple, and you will see that your answer is very sensitive to the initial temperature. Okay. This is one example. Now, another example is the same equation is taken it further and imposed the variation in the solar radiation, cyclic variation, which represents the either the 20,000 or the 40,000 or the 100,000 year cycle of variation. Okay. And is 1 minus albedo, and that albedo has that tan hyperbolic function. Okay. And then you have this outgoing longer radiation, and you have a white noise. This white noise is noise supplied to the system which has no preferred frequency. So, if the noise occurs at all frequencies, it is called a white noise. So, if you solve this equation, it can be shown that either you will get a solution which is periodic according to this forcing cos omega t, or it will jump between the snowball state and the present climate at random. Okay. So, and this depends upon the value of this noise. Okay. If there is no noise, it sits in the, it follows this simple law. Okay. If there is a slight amount of noise, here is 0.32, then it starts fluctuating between the two states. Okay. So, this shows the role of random noise, random perturbation on the solution of a nonlinear equation. This equation is nonlinear both because of the outgoing longer radiation as well as the albedo function. Now, in this paper, the author has given various values of A is the amplitude of the solar radiation and small a is the noise amplitude. And you can say if there is no noise, there is no stochastic resonance. Okay. If the noise is only 0.22, no. As soon as it goes to 0.26, it jumps, it starts having stochastic resonance. Okay. And if the noise is too high also, there is no stochastic resonance, and if there is no forcing solar amplitude also, there is no stochastic resonance. So, you can see that it is a very interesting example. You can see that he gets stochastic resonance if and only if there is a small amplitude variation of the incoming solar radiation and the noise is in a certain range. If the noise is too large or too small, it does not happen. So, there is a narrow range of noise amplitude during which the stochastic resonance takes place. So, this to me is a very nice illustration of the role of noise in a nonlinear system. Okay. Remember that this will not happen if this system was linear. If this alpha was a constant and this was linear, nothing will happen. Okay. System will just follow whatever forcing is there. Because the system nonlinearity is there through albedo and OLR, a small amount of white noise is sufficient to trigger this oscillation. Okay, the other issue that I want to briefly mention, which I will talk about later in more detail, is that we also should worry about the location of the continents. Okay, because the presence of landmass high altitude is a prerequisite for development of large ice sheets. Okay. So, if there was only ocean at polar regions, ice cannot form easily, because ocean is a large thermal inertia, is a large mixing layer, so it will not easily form ice. In land, forming ice is very easy, and so the configuration of the continent is relevant. Now, this issue is important because if you look at the data of the last 5 million years, the continents were not in the same location as it is today. Okay. So, if you see how ice ages had a 41,000 year cycle 5 million years ago, but in the last million years they have 100,000 year cycle. One of the reasons could be that the continental configuration was not same. Okay. So, this point will come to later when we discuss the snowball Earth. Okay. Now, the other issue to remember that at 65 north near polar region, obliquity or the tilt accounts for about 1/3 of the radiation variability. Okay. And precision is 2/3, and precision impact depends on eccentricity. Effect of eccentricity direct is small, but it regulates the precision. Okay. So, right now the Earth's orbit is almost circular. Okay. So, the effect of precision is not large now, but a long time ago when eccentricity was large, precision played a very important role. That is why you see that in the period between 1 million year and 5 million years, we had a 41,000 year cycle. Okay. So, the obliquity role also depends upon how eccentric the orbit is. If the orbit is more eccentric, its effect on precision dominates over its effect on obliquity. So people have examined when will the next ice age occur. Okay, there are a lot of debates. If human beings had not had interfered with global climate by increasing carbon dioxide, expectation is that the next ice age will come around 50,000 years from today. Okay, but there is an argument that on account of the increase in carbon dioxide from 280 parts per million to now 420 parts per million, the chances of the next ice age coming 50,000 years from now is very, very low. Okay. So this closes the discussion on the ice age cycles. To briefly summarize, we saw that the amount of radiation falling in the polar region during summer has a critical role to play, and that is the Milankovitch hypothesis. But that hypothesis cannot fully explain why we have 100,000 year ice age periodicity in the last million years, and to explain that we need to invoke a nonlinear phenomena. One of them could be stochastic resonance, as we saw in the animation, or it could be due to the land ice depressing the continent and that causing a delay in the ice age. So there are various hypotheses, none of them have been fully accepted, but we all agree that the trigger for the ice age is the incoming solar radiation. But when the actual ice age ends or starts depends on some nonlinear phenomena which we have not fully understood yet. Okay. Now the next topic we are going to take up is understanding what happened during the last ice age, which is very important to understand the role of carbon dioxide. Okay. Now if you recall, in the 1 million year data we have from ice core, the carbon dioxide and the temperature in Antarctica varied almost together. Okay. So from that data set we could not show whether it is the temperature increase which caused the CO2 to go up or the CO2 increase caused the temperature to go up. That was not resolved. For that we need a much higher resolution data set, and that was obtained recently from all these ice cores in mountain glaciers and Himalayas, in South America, Greenland, Kilimanjaro and Antarctica. So lots of data has been taken in the last 40 years, and in addition to all these ice core data, we also have data from ocean cores, okay, which go for a much longer period. The ice core data gets at the most up to 800,000 years, but the ocean cores can go to millions of years because you can drill as deep into the ocean as possible to look at all the deposits. Okay. Now I want to remind you that we are talking about changes in ice ages due to orbital variation, in which we are talking about scales of 10,000 to 100,000 year cycle, while most of us only external forcing we know is the seasonal cycle. We know that we have one winter and summer in most places where we live because the Earth's axis is tilted, and that causes the seasonal cycle of the incoming radiation. But there are many other things going on in the Earth which is not dependent on external forcing. We saw the DO events, Heinrich events. There are decadal variations of Atlantic meridional oscillation and Pacific decadal oscillations, and El Nino phenomena in the Pacific. All these are internally forced, internal variation. Okay. So now we are going to look at timescales of the order of thousands of years to understand why those sudden changes take place and what role carbon dioxide plays. So remind you once more that from the Vostok ice core, all we could say was the changes in carbon dioxide and methane were very close to changes in temperature. We could not say which was leading, which was lagging. Okay. Now to show that more clearly, this figure is superimposed CO2 and temperature over the last 800,000 years, and you can see that we cannot really differentiate much. One more graph, this also shows it has slightly different scale. Red is the carbon dioxide, blue is the temperature. You can see the peaks of carbon dioxide coincide with the peaks in temperature, and from this figure we cannot conclude whether carbon dioxide caused increase in temperature or the increase in temperature caused the carbon dioxide to go up. That we cannot resolve with the ice core data. So we needed much more accurate data. So in the last 10-20 years, people obtained very high quality, high resolution data during the last 20,000 years. Okay. So in the last 20,000 years, we have a lot more data. From there, we should see whether we can resolve this issue. So the question is, did the change in temperature occur on account of the increase in greenhouse gases like CO2 and methane, or the other way around? This is important to understand because many people have argued that the increase in carbon dioxide during the past 150 years could have been on account of increase in temperature and not the other way around. Okay. So they argued that CO2 went up because temperature went up and CO2 dissolved in the ocean just came out. Okay. So to resolve this, we look at a very accurate database, and this was a famous paper published by Jeremy Shukun in Nature 12 years ago. Okay, very important paper. That's why I want to spend some time discussing this paper. So they look at all kinds of cores all over the world, the Antarctic ice cores, Arctic ice core, lots of ocean core data all over the place. Okay, using various proxies, magnesium by calcium ratio for temperature, and then microfossils, pollen, all kinds of different proxies were used to find out the temperature variation as well as carbon dioxide variation in the ice core bubbles. Okay. Now notice that the cores are not uniformly distributed around the globe. There are lots of gaps here in the Indian Ocean, in the Atlantic Ocean, in the Pacific Ocean. There are no ice core data. We cannot do much about that. Okay. So the challenge was to take all these different data, proxy data, for the last 20,000 years, and to combine them to get a global mean temperature. Okay. Now that's tough because you don't have much data in these regions. Okay. So you have to somehow convince people that data average over all these cores will give you the correct global mean temperature. Okay. And today, of course, you have the advantage that there are simulations by climate models which simulates temperature from 20,000 years ago to today. Okay. So those climate models tell you whether this set of observations are sufficient to estimate the global mean temperature accurately. So that is the challenge that we need. So we'll continue this discussion in the next lecture.